So last time we were looking at the construction of bus impedance matrix, right? So when we were looking at that, we had already looked at how to construct the bus admittance matrix or the Y bus. So again, the question that you should ask yourself, or if you are not able to ask, if you are not able to find that answer with yourself, probably you should ask me or you should ask your teacher, is that why do we need the bus impedance matrix, right? And the answer is that when we are looking at fault analysis and when we are trying to calculate the fault current, we are looking at the effective Thevenin equivalent circuit at the point where fault occurred, right? So we will convert everything else at the point, the complete grid across the point where the fault occurs as its Thevenin equivalent. And it's not easy to calculate the Thevenin's equivalent of a huge grid. So that is where the set bus comes into picture, right? So we had looked at the physical significance of different values, right? We found that the diagonal element that set I corresponds to Thevenin's equivalent impedance at node I, and set Ij corresponds to the voltage increase at node I for the current increase at node J, right? So I hope you remember all this, right? Then we looked at the concept of branch, right? So branch is any element that we add into so what basically the idea of doing a what you call as building a set bus matrix is that you will be given the one line diagram of the grid. What we do is that we take element by element and we add it to the network and to the matrix, right? So branch is an element that ends up creating a new node in the diagram and a new row and a column in the matrix. So basically first we will add z is equal to z0 1. So it's always better, it's always good to start with reference, right? So here the reference is ground. Suppose we are having a grid which does not have a reference, which does not have a reference to, means does not have any shunt connection, then probably we will be forced to take one of the buses as reference bus, right? Then we were adding, when we had to add the second element, what we did was that, okay, we saw which node this to which existing node is this element connected to. So it is connected to 1. So what we did was that we repeated the row and column for 1, and to the diagonal element of 1 we added the value corresponding to the new element, right? Similarly, we looked at the third element. We added the value of the new element, right? So that's how we got this matrix, right? Also, we looked at what happens when we are adding an element which is not connected to which is connected to reference node instead of other existing node. So in that case, since it's getting connected to reference node, what we do is that we make all the 0 and then we do Z04. So is this clear so far? Is that clear so far for you guys? All right. I'll just put a poll over here for my just convenience. Right. Thank you. Right. Okay. So what we will do is right now we will just let's just do a problem. Okay. Then we will proceed. Okay. Let's do one problem to refresh just to see if you have the concept clear. Okay. So we are looking at a 3-bus system. So we have three buses, right? So this is A.8. J0.8, this is J1.2. This is a very straightforward easy problem, right? But this is just to ensure that you guys have that clarity, right? Okay. So it is the line impedances. Impedances are given. All right, let's not make it. Find the subset bus. Okay. Probably okay, I'll give you 2 minutes of time to do this, right? So if you're done, just let me know in the chat window, right? So did all of you get this? Okay, so that's 4 years. Okay, good. So this is so far so good, right? Okay. Now let's look at, so right now what we were trying to achieve so far was that, okay, we're trying to build the skeleton of the system. Now, what if there is, so suppose this is, at the end of the day, this is like just like adding one line, and this ended up creating a new node, right? What if we are going to add a line between two existing nodes, right? Then what should happen? The size of the matrix should not change, right? So let's look at that condition, right? Yeah. So, okay. Are you able to see my screen? Yes, you are able to see my screen. Right. Okay. This is so now we have, say, suppose four buses. Three buses. One, two, again three, the same thing. So this is where we started, right? 0, 1, 2, 3. So we have, okay, we have these. This is our grid. Now we are going to add one more element between 1 and 3. Or let's make it between 1 and 3. So, okay. So suppose there is an interconnection between 1 and 3. How does it affect, right? This also can happen, right? So there is between 1 and 3, right? So, okay. So set 0, 1, set 1, 2, set 2, 3, and set 1, 3. So the existing set bus would be, before we add this line, it would be set 0, 1, set 0, 1, 0, 1, right? Then 0, 1, set 0, 1 plus set 0, 2, set 0, 1, sorry, set 1, 2, 0, 1 plus set 1, 2, right? Then again set 0, 1, then set 0, 1 plus set 1, 2, then set 0, 1 plus set 1, 2 plus 2, 3. All right. Okay. So this would be the matrix. Now we are going to add this new element set 1, 3, right? So what we need to do is that we need to create a new row and a new column, right? Temporarily. We'll create a new row and a new column temporarily. So this is like creating a temporary bus. So 0, 1, 0, 1, 0, 1. Okay. So then we are going to create a temporary bus called as L, right? And this is going to be, so this would be set 1L, set 2L, set 3L, right? And set L1, set L2, set L3, and set LL. Okay? Where set Li, this one, right, would be set Pi minus set Qi. Okay. Now suppose we are connecting this new element between P and Q. So in our case, what would P and Q be? P would be 1, Q would be 3. Okay. So this element would be, set L1 would be set this minus this, right? This element would be this minus this, and this element would be this element minus this. Similarly, this element would be this element minus this element minus this, and this element minus this, right? And set LL, okay. Also, just let me know if you need time to note this down, right? I'm assuming that you're noting down in parallel. This is one of the problems that we may have in an online class. I can't see you guys writing down, so I don't know what pace you're going at. So if I am going from one slide to another quick, just let me know. I can slow down. All right. Right. And the diagonal element ZLL is given by ZPP plus ZQQ minus OZPQ, right? Plus PL, right? Um, but this is the impedance of new element. So basically what we are saying is that say suppose this new element is getting connected between 1 and 3, then we take the diagonal element of 1, diagonal element of 3, then we subtract set 1 3, the existing set 1 3, and then add the new element. So that would be your set LL, right? So right, then you calculate. This is the set bus building is actually kind of tricky. That's why set modified is equal to, or we will look at a problem, set old minus set li into set jl, sorry, set lj, or set jl divided by set ll. So basically this will be a 3 cross 1 matrix, and this would be a 1 cross 3 matrix. So the product will be 3 cross 3. This would be 3 cross 3. This is already 3 cross 3. So it will give you a 3 cross 3 matrix, right? I know this can be a bit confusing. Let's let's just look at a problem, then that way it will be easy, right? Okay. Trying to share my screen and it is actually not working. Okay. Right. Okay. Let's look at a question that may help. Let's okay. Mm, let's just add to the old problem itself, right? Right. So we have a 3 bus. To this, let's add one new element between 1 and 3, right? And put it as okay, 1, right? Okay. So, okay, what was the set bus value we got earlier? Okay, so the set bus value that we got earlier was 0.8. Okay, let's do J out. Okay, 0.8, 0.8, 0.8, then 0.8, 2, 2, 0.8, 2, 4. Right? Am I correct? Right? So then now we are going to add temporary. Okay. Now I'm going to add a temporary. Okay. So what did I say? So what is P over here? P is equal to 1. Q is equal to 3. Right? Set PL. The new value of the new element that is getting added is J1. Right? What is set PP? Set PP is 0.8. Set QQ 4. Right? Right. Now let's look. What would be this one? This is this minus this. That is 0. This minus this. That is minus 1.2. And this would be minus 3.2. Right? Correct? Same here. 0 minus 1.2 minus 3.2. Correct? Okay. Then mm, what would be ZLL? That would be point. Okay. That would be equal to 0.8 plus 4 minus 2 into what is Z13? Z13 is 0.8, right? 0.8 plus 1, right? So what would that be? 4 minus 0.8, 5 minus 0.8, right? 5 minus 0.8 is 4.2, right? Is that correct? 5 minus 0.8, 4.2. 1 by 4.2, right? 1 by 4.2. There is a j whole, like this whole equation we will put in a j. Okay? Right now there is always j. Don't forget that. Right now, it's for the sake of calculation, I'm not putting it there. Right? And 3 cross 1. Zero minus 1.2 minus 3.2, right? Into 0 minus 1.2 minus 3.2. cross 1 and 1 cross 3, right? Can you do this calculation and let me know what this value is? Should be 0 0.8, 0 0.8, 0 0.8, 0 0.822, 0 0.824, right? Then okay, then first row, second row into second column, so that is minus, so it's 1.44, correct? And 32 3.2 into 1.2, so that is 3.84, right? So this would be again 3.84, one of the better parts of matrix multiplication of symmetric matrices, divided by 4.2, right? So what would that be? 1.44, 0.342. Okay, this is 0.342. That would be 0.342, and what would be this one? Point 9, rounding it, okay, 0.914. So this is after division by 4.2. Okay? So if we calculate, it would be Z bus is right, and this is 2 minus 3.42. 342. So guys, okay, fine. Can you tell me what mistake I made over here? Can somebody tell me what is the mistake that I made over here? Yeah, thank you. That's at least, yeah, that's good. It's 3.2 square. This should be 3.2 square, right? So what is 3.2 square? 3.2 into 3.2, that is 10.24. Again, I have to divide it by 4.2, right? And if I subtract that, okay, that is 2.43. 2.43, right? And if I subtract that from 4, it is 1.56, right? And if I subtract 2 minus 3.84, okay. Is this clear? Does it makes, is that clear? Also look at what happened over here. When you made the network more interconnected, right? That effective change in voltage and the Thevenin's equivalent also, Thevenin's equivalent. So what happened? We are creating more parallel paths, right? When we created more parallel paths, the effective Thevenin's equivalent also reduced because at that point there are now multiple paths and there are, when you're taking the Thevenin's equivalent, it will come as parallel and effectively the value comes down, right? Earlier, if you see without that line, this was 4 and this was 2. Now it has come down because there are parallel paths now, right? Does that make sense? Am I audible? I'm audible, right? Okay. You see, the problem is that don't, I will not be able to understand what problems you're going unless and until you voice it. Okay? So please feel free to voice it. There is no thing called as, you should not have any inhibition over here, right? I'm also looking for any kind of feedback that you have. You can give it right over here. There's no problem in that. So if you don't understand, we'll look at one more problem, right? Okay, so this is one thing. Let's do one, let's take one more step, okay? Let's try to reverse this whole thing. Um, so suppose, I don't know if you remember where we removed a transmission line from Y bus. You just had to subtract it from, I still have it. So if we were removing one uh, line from a transmission Y bus, you just had to subtract it from the off diagonal elements as well as you have set the off diagonal elements to 0 corresponding to that element and you have subtract that value from the diagonal element. But here what you are going to do is that you are going to add a minus z element. So suppose you want to remove a transmission line. So suppose now we added this 1 3, right? Suppose we want to remove it. What we will do is that to this matrix, suppose now we have this grid and we are saying that we are going to remove this j 1.0, right? So the set bus corresponding to this was this. Now we are going to say that we are going to remove j 1.0. So what we do is that instead of here, everything is same. It is like creating a new, adding a new link, but instead here of set PL we'll take minus set PL. We'll take the negative value. Is that clear? I'll just make a note of it so that. So we're talking about removing a link, right? You can't remove a branch because suppose there is only one connection to a branch, you'll end up removing a row and a column. So it is not ideal to remove a branch. So removing a branch means if removing an element will end up islanding one node, then you should not do it. So suppose, okay, here in this given scenario, you can remove any line. You can remove any of these 3 lines, right? You can remove any of these 3 lines. That is fine because even if you remove any line, there is one connection to all the buses, right? Suppose you remove this, then you cannot remove this line or this line, because then it will create an island. Clear? Okay. Okay. So the process of removing a link is same, right? Right? Everything is same. So what we do is that set PL is equal to set PI minus set QI, right? Then set LL would be PL. Sorry, this one is not set PL. This is set LI, right? Set PL. Is this clear? Is this clear? All right. Okay. Kora, is that clear for you, or is kind of everybody else responded? That's why I'm asking you. All right. Okay. Okay. So let's try reversing this. Let's see how that would happen, right? So, so what is the grid that we have right now? Sorry, my network got stuck for a minute over there. I'm really sorry about that. So suppose right now we have 1, 2, 3, 0. So this is point it, everything is J, okay? Don't forget that this is 1.2, this is 2, and this is 1, right? And we got the set bus for this network as 0 0.8, 0 0.8, 0 0.8, right? So what is 0 0.8? It's 0 0.8. This is 0 0.8, this is 0 0.8, and what was the value we got over here? 1.658. 0.658, and this is 1.84. This is also 1.84, and this is 1.6, 1.56. Yeah. So now let's try reversing. Let's try removing 1, right? So what I would recommend is that while I'm doing this, please try to do this along with me on your own, right? You have now the idea, right? Just try to do this on your own, and let's see if you are able to get it, right? So again, this would be 0. This would be 1 minus 1.84. It would be minus 1.04, and this would be 1.6, so that would be 0.94 minus 0.94, right? So 0.76, my bad. So anything same over here, 0 minus 1.04 minus 0.76. Okay, and this value would be 0.8 plus 1.658 minus 1.6 minus 1, right? And that would be that minus 0.142. Okay, I have a message. Okay. Yeah, thank you. Sakura, sorry, I just saw your message right now. Is that okay? Like, this is correct, minus 1.42. What did you want me to repeat? Okay. Yeah, so, okay. Okay. Is that clear right now, or do you want me to repeat the procedure? All right. So now let's set this, right? So this would be, I'm writing these numbers. I thought I'll just prepare the slide, but the problem is that I want you to grasp the idea of how the numbers are proceeding. And there is actually a beauty to this if you see. The values corresponding to the first bus is not getting affected at all. You see at all, uh, the Thevenin's equivalent with respect to that is not at all changing because there is no grid beyond it. The only connection that has to beyond that is, suppose there is, if there was a grid connection, if there was a shunt at any other bus, this value also would have been affected. Okay. This 1.58, 1.84, 1.84, 1.56, then minus, that would become plus, right? 1 by 0.142, right? And 0 minus 1. So if you multiply that, you will get, okay, give me a second. Okay, so I please start doing the calculation, right? I'll also do this in parallel. Okay. So are you guys getting the value? So it will be this 0, 0, 0, 0, and 0, right? Divided by 0.14. Okay. There is some mistake in the calculation. It is back as 2. What did we go wrong? Let us correct. This is also correct. 0.76, 0.8 plus 1.658 minus 1 plus 1.6. 0.8 plus 1.658, 2 plus 1.6 minus 1, 3.508. Okay, so in that case, when I divide this, it will get 3.08. Okay, 1.04 divided by into 1.04 divided by 3.05. Come as 0.353. This was 0.76. Right. So again, this is 0.76 into 0.04 divided by 3.056. No, right? I'll just check and we'll revisit this problem later. Okay. I think this is coming. This should actually come as 2 point something, but it's not coming as 2 point something. Yeah, something wrong in the calculation that I did right now. Okay, previous slide. Right. Okay. 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 Yeah. Took the value set 2 instead of set 3. It makes more sense. Wait. Let me do something. Let's hold this problem over here. The process of removing the line, we will revisit again in the next class. I'll just confirm this and I'll get back to you because whatever notes I am having, doesn't feel clear to me. Okay. Let me just give you one problem. You guys try this out. In the meantime, I will in my parallelly try to do Okay, so one more thing over here. Say suppose you are adding say suppose instead of this J1 being like this, if it is between this, say suppose you have an existing grid, and the new element that you are adding is between ground, say suppose. Right. So if you are adding a new element, it's the same, shunt is same, but what will happen is that P will be considered as 0. So basically, whatever we wrote, right, that Li would be 0 minus set Qi, right? And set LL would be 0 plus set QQ minus set QQ. And if there is already existing shunt, you can add that value. But if there is no shunt, that is minus 2 Z0Q plus Z0Q new. So basically, when you're if you're building a set bus thing, it's always better to keep the shunts, except for the first shunt, first shunt, everything else to the end, because this calculation is easier. If you add shunt and create the node, then adding this as a link will be difficult, right? So if you have a choice, always create a branch between two existing nodes rather than a reference node, because this adding a link towards the end is more easier, right? Let's look at a few questions before we proceed. Can you calculate the signals? You calculate the set bus for this one. you're done, just let me know in the comment section. Okay. Are you guys done? I'll just start writing the answer. Okay. So the set bus would be, there is a J, don't forget that. 4, okay. 0.2, 0.2, 0.2 and 0.2. Right? And this is 1.2, 1.2, 0.2, 2, and 2, 2, and this would be, then this connected to 2, so this will be 0.2, 0.2, and 0.7. So is this the answer you got? Okay, so few people did not. So what was the difference that you got? Wait, I think. Yeah, I think the solution probably. This is from a solution question bank that I have. Maybe the solution is wrong. Let me just write it on my own thing. That will be easier, right? Yeah, I'll explain. Give me a second. Probably that solution that I wrote might be wrong because this is directly from a question bank, so I did not write the solution. So yeah, let's add the first element. This is 0.2. Then we are going to add element number 2, right? What is element number 2? So element number 2 is connected to 1. So we are going to repeat it, 0.2, and we are going to add water 16. Then we are going to add element number 3. Element number 3 is connected to 2. So we are going to repeat this. So this is 0.2, 1, 0.2, 1. And we are going to add whatever is existing. Now element number 4 is connected to 1. So we need to repeat the row for row number. Is this the answer you guys got? Is this clear? I think that solution is wrong. That whatever I have in my notebook is wrong. Means in the booklet is wrong. Because okay. So so Takora, it's also clear, right? Okay. Let's do one more question, right? This actually will test whether you have understood the concept that we have been trying to explain so far, right? Yeah. So look at this question. It says for a power system network, the Z33 is given as J0.5 and the voltage at the node is 1.3 angle 10, right? So now they are connected a capacitor having reactance minus J3.5 per U to the between node 3 and reference node, right? Now they are asking to calculate the current drawn by the capacitor. Can you do that? I'll give you 2 minutes. So remember what Z33 is, what that is, then it will be very easy. So here they have just given one value of Z33 and they are asking you and now they are saying that they are adding one new element, right? And they are asking you to calculate the current drawn by that element. Are you able to crack this or do you need me to explain? So I'll just put a quick poll. You can click that yes and no. If you are able to proceed, I won't explain for another 2 minutes. Or if you want my help, I will. This is one of those interesting gate problems that actually you probably will not be able to attempt if you don't know the concept, and if you know the concept, you can solve it in a minute. It's that straightforward. It's just few calculations, right? Hmm, I'll give you 2 moments up to 6:20. In the meantime, if you are done, just let me know in the comment section. Mm, I was able to do it. Okay, so one thing, Tagora, the current would be what you call as a complex number, because we are dealing with complex quantities, right? Yes. Uh, Correct answer is 4.43 angle 80. Yes, that's the correct answer. Shall I try to solve this? What about Varun and Mahak? Okay, fine. I'll just show you, explain to you why or what this is, right? So what have they given? They have given with 33 equal to 8.5. Now, what is this? This is evidence equivalent impedance. Basically, see, even though this is a looks like a power system question, basically this is a network theory question. So what they have given is that VTH is 1.3 angle minus 10 and ZTH is J 0.5. Now they are saying they are connecting a capacitor minus J 3.5 per unit, right? So basically, what does Z33 mean? It means if this is node 3, this is the Thevenin's equivalent impedance and this is the Thevenin's equivalent voltage. So what would be the current flowing through this? It is basically 1.3 angle minus 10 divided by, so this is JJ, right? So this is minus 3 angle 90. So if you divide, you will get 0.43 angle 80. See, that simple problem. Is that clear? Does that make sense? So see, they won't ask this question in network 3. So if they have to frame this question as a network 3 question, it will be like Thevenin's equivalent impedance is 0.5, Thevenin's equivalent voltage is 1.3, a capacitor is now connected across it. What is the current flowing through the capacitor? It is basically the same question. Now they have framed it in the form of a power system question, right? Okay, then one last question that we would do before we wind up for today is, okay, let's look at this one. Not this one. This is J.4, this is J.4, okay, this is J.8 and this is J.2. Yeah, calculate the Z bus. So start doing this properly, okay, and I'll also just write down the answer on the next page. Point 4, 0.2, 0.4. Do you want to see that network diagram? Okay, so please, yeah, always preferably draw it down. So just do this problem. We will continue from this problem in the next class. Okay? So try to finish it, and we will compare the answers in the next class. And also we will revisit one problem from removing the transmission line also. Then we will proceed to the concept of power generation. Is that okay? Please do this problem for the next class. Okay? Just continue. Even so, the thing is that I'm winding up the class at 6:30 today. But just make sure that you guys finish this question so that we can pick it up from there tomorrow, next class. Right? Yeah, so happy weekend to you guys. I think you guys have classes all over the weekend. You know, it's a little strenuous, but yeah. But if you give, see, at the end of the day, uh, gate is predominantly your effort. That you have to put in as much effort as you can, but don't burn out yourself. That's also one thing. But yeah, have a proper plan schedule and work according to that schedule, such a way that you cover all subjects. You are able to revise the topics a bit, and you're able to revise the topics, just the important points, and do as many questions as possible, right? After this, because see, we also, I think, IIT's gate class also provides you mock examinations. Also sign up for other institutes exams also if you can, or you can share between yourselves. Like once you are in, like if you're comfortable with each other, you can take sorry, do as much test as possible. That will help you in the long run. Okay. Anyway, all the best and happy weekend. So I'm going to end the session. Do you have any questions as of now? This one? Oh, the answers, right? The one that I was working on. Okay, this one, right? This is actually wrong. This is not 3.4. This will be 0.4. The 0.4, this would be corresponding to, right? So this is the matrix corresponding to this grid. You wanted this. Sorry, Takurakas. Can you tell me which slide you're looking for? So I'm going to close the session, and thanks for your time, right? Right. Thanks a lot. Right. So yeah. So last time we were looking at the construction of bus impedance matrix, right? So when we were looking at that, we had already looked at how to construct the bus admittance matrix or the Y bus. So again, the question that you should ask yourself, or if you are not able to ask, if you are not able to find that answer with yourself, probably you should ask me or you should ask your teacher, is that why do we need the bus impedance matrix, right? And the answer is that when we are looking at fault analysis and when we are trying to calculate the fault current, we are looking at the effective Thevenin's equivalent circuit at the point where fault occurred, right? So we will convert everything else at the point, the complete grid across the point where the fault occurs as its Thevenin's equivalent. And it's not easy to calculate the Thevenin's equivalent of a huge grid. So that is where the set bus comes into picture, right? So we had looked at the physical significance of different values, right? We found that the diagonal element that set I corresponds to Thevenin's equivalent impedance at node I, and set Ij corresponds to the voltage increase at node I for the current increase at node J, right? So I hope you remember all this, right? Then we looked at the concept of branch, right? So branch is any element that we add into so what basically the idea of doing a what you call as building a set bus matrix is that you will be given the one line diagram of a grid. So what we do is that we take element by element and we add it to the network and to the matrix, right? So branch is an element that ends up creating a new node in the diagram and a new row and a column in the matrix. So basically, first we will add z is equal to z0 1. So it's always better. It's always good to start with reference, right? So here the reference is ground. Suppose we are having a grid which does not have a reference, which does not have a reference to, means does not have any shunt connection, then probably we will be forced to take one of the buses as reference bus, right? Then we were adding, when we had to add the second element, what we did was that, okay, we saw which node this, to which existing node is this element connected to. So it is connected to 1. So what we did was that we repeated the row and column for 1, and to the diagonal element of 1, we added the value corresponding to the new element, right? Similarly, we looked at the third element